We don't learn math, we just get used to it. So you just get used to this kind of math. All right, so I just want to go over this just one more time so you can see it. Here's f of x equals x squared. The way I've drawn it is topologically equivalent to x squared. Here's the y values between 0 to 1. So you draw that, and then you figure out what x values gave you that particular range or that image. And the x values that gave you that image are going to be the ones between -1 to 1. So when you get one of these in the book, I'm going to give you some exercises where you're actually just reading the book and trying to figure out what he's trying to say. Bartle's not a good book, actually. There's better books that have been written. But sometimes it's good to teach out of a bad book because you have to decipher what he's saying. And you get used to reading things that are hard. And one of the things that it's done for me is that I feel like empowered that I can read anything and figure it out. If I can read these books and figure things out, I can just jump field and do work in nutrition and exercise physiology and read myself and figure things out. So it's a very empowering feeling. True, right? Filling in those gaps. So f inverse of h is a set. It's the interval -1 to 1. I kind of told you this already. Subset of A. How do I know that? Because it says the elements must belong to A. Members of the set belong to A, so f inverse of h is a subset of A. Okay, so you have a homework assignment on countably infinite, so don't put any finite sets as your examples there. Somebody's going to do it, but I'm just going to tell you right now, if you have to watch the recording again and say, I'm not going to put any finite things as my example for countably infinite, because we just say countable. But we say a set is countable if there's a bijection from n onto s. And s is not countable, we say it's uncountable. And this symbol here just means there exists this backward thing. I didn't think there were people that actually still did set theory, but I met someone who was a set theorist at the joint math meetings. Some people get really enamored by countable and countably infinites and sets, and they just stop there and they say, I'm just going to specialize in set theory. There used to be a lot of them.
When in grad school for my master's, there was definitely a set theorist, and she didn't do anything else.
Yeah, it's strange.
What is there left to find? I thought we were like all onto like groups and categories and stuff.
You can actually get specialized in set theory. Like I said, it's not the wave right now, but I was taught by set theorists, so they exist. All right, the even natural numbers are countable. This should seem obvious, but the bijection, so the evens are going to be the multiples of 2. This is how we define an even number. And the bijection that I'm going to show you is actually a bijection. Is f of n equals 2n. And f goes from the natural numbers to e. I've got everything defined. In your book, he has a proof. It's a little hand wavy that the rationals are countable. So it's in your book. It's the one that Dr. Calkin did with the mappings, where he just drew the grid and then mapped every one of the rationals up. Yeah. All right, so I'm going to prove this for you. I have a proof writing guide. I generally don't use it for real analysis, but I'm going to pass it out. Alma Cooper was always like telling me, just let's go back to that proof writing guide. Write down what you know, write down what you have to show, and then start putting that proof together. And she's absolutely right. So in her memory, we're going to actually go to first principles. I'm not going to do it right here. Maybe I should. I'll do it on the board. You guys all see that board over here? Function. So this is the definition of being one-to-one. And anything between the if and the then gets popped up into your no. So revise no. So this part here pops up into your notes. So these are all facts that you can use. And this is your goal. You're trying to get this to be your last line of your proof. So this is a shortened version of writing down all the things that you can use. I have to assume f of n equals f of m, and I have to show n equals m without telling anybody that my n and m live in z, which I should have done. So assume that. By definition of f of n is 2n, and f of m is 2m. So 2n equals 2m by pulling that thing from my no that says f of n equals f of m. By canceling the 2 from both sides, I get n is equal to m as desired. So this is a short proof. It's, I think, not even a foundations level proof. It's like a discrete math proof. Correct, Bridget? I think discrete math should go away. There's no need for it. Put them straight into topology.
Oh, yeah. That's good. Yeah.
Okay, good. Everybody have this down? Okay, surjective, onto. Onto is always a little bit harder. I'm not going to put the no and the show up on the board. I have a little bit of this here. I start out with a Y in the, I forgot what they call it, direct image. So every book uses a different name for these things. That's why I'm struggling a little bit. Y is in the direct image. I need to show there exists an x in the domain, such that f of x equals y. So if you think of something that's not one-to-one, like your y equals x squared that's on the boards, I had r to r, I can find an element in the, it's not in the direct image, but this is the range. I think that's what he calls it. So I can find an element in the range, -1, that doesn't have an x that leads up to that -1. So that's not one-to-one. Here, and think of things that are one-to-one, like y equals x cubed. For every y value in the real line, I can find an x value that directly can be paired to that y value. So in this case, I'm going to show the same thing. This is the verbiage for onto. If y belongs to the range, then by definition of the way we define the range, y is equal to 2n for some n belonging to n. By definition of f of n is 2n. By setting x equal to n, we see f of x equals y. So for every element in the range, I can find an element in the domain such that it can be paired to. And I should have put Z, not N. If you think about it, it is pretty wild. Like there's as many things in the even numbers. You'd think there should be less. There's as many things in the even numbers as there is for all the integers. That's the thing you tell the kids in the back of the car. All right, I told you this already, but the rationals are countable. We'll have a day where we're struggling, and that day we'll watch Dr. Calkins talk. It's just such a nice talk. But the proofs are pretty easy. There's a hand wavy one in your book. The real line is not countable. I do have a proof using metric spaces, I think. I think we use little balls and show that cannot be a bijection. Maybe Dr. Moan can find a good, easy one. I don't know, like if there's an easy proof to show that the R is not countable. I remember seeing them.
I have one that's
Is there the diagonal one?
For the rationals, yeah. The diagonal one is in your book. That's the one that's in your book. So that means that even though Q and R are super, super related to each other, closing up all those limit points ended up with something that's not countable. Like you can't put your finger on 1, 2, 3, and actually like put a dot to each one of them, which is really amazing. All right, so round.